simulating surface-enhanced Raman scattering using ADF. So I'm going to briefly describe a little bit about methodology. So it's fair to mention this discrete interaction model, and I'll show you a little bit about how to set up the simulations, a little bit of discussion about input-output, and some recent results based on this approach. It seems like there are several people that have trouble hearing. Is that the case? Is there still issues with the voice? Or is this okay? Is better? Okay, I'm going to assume that this works. Fine. So the brief introduction about surface-enhanced Raman scattering using this model. Okay. So the general principle of surface-enhanced Raman scattering, the isolate oxide surface plasmons, the metal nanoparticles appear illustrated on this. The analyte on solar crevices or small junctions in these metal nanoparticles, they generate huge electric fields near the surface. And based on this, you can actually enhance spectroscopy, sort of Raman scattering, Raman scattering, Raman optical activity, and fluorescence, IR. And Raman scattering is going to be the main topic of this webinar. The main interest is that you can have this million-fold type enhancement all the way up to 10 to 14, depending on how you actually count your numbers. So the limit we can do single molecule detection using Raman scattering, which means SERS gives you the ability to actually detect a single molecule and identify it. And the main common mechanism is this electromagnetic mechanism, which the simplest way of thinking about this, considering the two objects as two polarizable objects that interact with each other. If you do that, you can write down total polarizability for the system, here given by these expressions here, where alpha M is the polarizability of the molecule, and alpha NP is the polarizability of nanoparticle. And you have a distance-dependent coupling term, this is the separation between these two. If you then look at the change in the total polarizability due to vibrations in the molecule, which is directly related to your intensity that you measure in Raman scattering on the show, you get terms that scales as the intensities you would expect from the free molecule times this additional factor that is the local field to false power. Okay, so the reason surface-enhanced Raman scattering gives you this large enhancement is this e to the 4 type dependence close to the surface. So what my group has been developing and was implemented into ADF is this discrete interaction model called mechanics for describing molecular plasmonics. And basically what it does is it couples our TDDFT description with the molecule with the metal nanoparticle and a class called electrodynamic simulations of this. Okay. So we're going to go a little bit into details about the methodology briefly, and then I'm going to show you one example that are available in ADF for our actually set these calculations and look at to the simulation. Okay. The main component for treating these metal nanoparticles, since we need to treat very large metal nanoparticles, to use an atomistic model that's called the discrete interaction model. So in this model, each of these atoms in metal nanoparticles is described either with a polarizability or capacitance or both. And if you then put in an oscillatory electric field, the polarizability will induce a dipole, and the capacitance will induce charges, and all these fluctuating dipoles and fluctuating charges will interact together. And the way you simply solve these set of equations is to write it as this dim equations in this way. So you set up a general response matrix that's based on the electric fields and potentials, and you actually generate these induced dipoles and induced charges. Okay. And there's a couple of different formalisms implemented in ADF. One where you only use possibilities, which typically are most suited for larger metal nanoparticles, and one where we both have capacitance and polarizabilities in there, which is most suited for small particles. And we're going to see an example where we use this polarizability only model called in. So the general way that it's coupled is through a QMM type formalism, where you have the energy of your QM part and you have your energy from the coupling between your QM part and the dim part. And both of these terms depends on the electron density. So you have, and you can, if you split it up, get in a QM term, you get a poor polarization term that again depends on the density. The terms describe the mutual polarization of the molecule to the metal nanoparticle and the metal nanoparticle to the molecule. And then you have a van der Waals terms as well. And here it's just, again, the polarization terms of electric field times this is classical energy due to an induced dipole and classical energy due to an induced charge. And the operator here, if you minimize this energy in the same way that you do the Hume energy, leads to an effective Coulomb Hamiltonian, where you have this additional dim QM operator in here that can become for minimizing this energy with respect to all parameters, which means also fluctuating dipoles and charges. So the van der Waals energy term that's implemented into the ADF and the M2M is based on a standard amber Lennard-Jones 612 potential given here, with one small modification is that certain systems, in order to describe binding sites at different bases on metal nanoparticles, there's actually a coordination-dependent Lennard-Jones parameters in here. So, example describing the nitrogen here or the purine molecule, its interactions with the silver atoms here depends on the local coordination environment of that silver atom in here. And that's sort of described here by this formula, which is just a linear interpolation, counting nearest neighbors and a little bit of the second shell as well, to give you a value between 1 and 12 for these sites, which means a coordination-dependent force field allows you to sort of differentiate binding between low coordination size and high coordination size. So the main focus of the DMQM model is response properties, which means this is implemented within TDFE, where again we set up the same type of time-dependent DFD equations to have for the free molecule, but you get one additional term due to this DMQM operator. And the simplest way to look at this DMQM operator is that it's sort of again the potential and for both the polarizability and these charges. So it's sort of like an image field type effect. Okay, the fact that your charge distribution of the molecule sees sort of an image in the metal nanoparticle and the interaction is in here. There is one additional term in here from the local field. So this is due to these plasma excitations, it generated strong local fields, which generated a new perturbation on that. Okay? So in your free molecule simulation, the external perturbation is only covered by here, but there's one additional term in here due to interactions from the external light on this metal nanoparticle. So you have to account for this. Okay. So if you want to consider the simplest way of looking at that is considering the external electric field induces a dipole into the molecule. The molecule induces a dipole into the metal nanoparticle, and that acts back this sort of image type field. And all of these solve cell consistently in these simulations. The other interactions is a local field where the external field induces dipole into the metal nanoparticle, which is sort of this plasmon excitation, and that local field operator will also perturb the molecule in here, which means every interaction in here is in fact all cell consistently, which means what you actually get out of the DIM-QM calculation of, for example, the polarizability, is the polarizability of the free molecule, whatever is induced into the molecule due to the nanoparticle, and what's induced into the nanoparticle due to the molecule. Which means all local field effects are actually folded in into the polarizability that comes out of the calculation. So in order to actually describe these properties, we have to use dam response theory, which has been implemented into ADF and the AO response package. The main difference from regular response theory is that there is this lifetime parameter in here. You can sort of think about this as excited state lifetime, and it just ensures that the total response is correct even when you're on resonance, which means you can calculate polarizabilities on resonance with that, and then just get it in the regular way. Okay, so you just get it from the dipole moment and the polarizability. Again, there is one extra additional operator here due to the local field induced by the external light into the metal nanoparticle that are not present in the regular system. Okay. So I'm going to show you a little bit about a small setup for doing N2 on small silver nanoparticles. This is an example that's found in the example folder in ADF. And there's sort of three blocks that are important for setting up a Raman calculation. We have discussed all the three: DIM-QM, DIM-PAR, and AO response. I'm going to shift to the graphical user interface here on it. I'm going to open now the input file for the DIM-QM. So what you see here is the beginnings, all the technical things that are familiar from running a standard ADF calculation. So definition of molecule basis, functional, SF, and integration accuracy. I'm going to focus on the three blocks that are unique to DIM-QMs. And the first one is the DIM-QM block key. So the first line here tells you which kind of model it is. So PIM is polarizable interaction models, means that it's only running using the polarizabilities. Linear equations can be pretty big, and here we specify which algorithm that we actually need to solve these linear equations, in this case direct, which means solving everything using the memory. There's a few different algorithms in here. There's also a choice called best that allows the machine to pick which one is appropriate based on the size of the system. There's a default screening that when you get close to the QM part, close to the middle nanoparticle to ensure that you don't get overpolarization. Here, this is taking the default parameters. The force field here is a Leonard-Jones. Where the specific parameters for both the coordination dependent of the silver is given here, and the chemisorption potential for nitrogen, so it allows you to sort of differentiate between these different binding sites to that. And we just specified this frequency-dependent calculation. We need to include these local field effects into this. So this is sort of the setup of specifying the specific model, the force field, and how to solve these linear equations, what type of interactions between the molecule and the metal you actually need. To specify which chemical system that you're actually looking at is all specified in the DIM hierarchy, where you have a subblock for each of your atoms. In this case, since this is a PIM model, you need to specify a radius, and you need to specify some way of finding frequency-dependent polarizability. In this case, it's based on a Drude type model for this. There is also a possibility to read in experimental functions and Drude Lorentzian type functions, so you can fit in most different type of dielectric content in here. But this is a simple Drude model that will have a resonance around 350 electron volt. The rest of it is actually just an XYZ file describing coordinates of the metal nanoparticle. You know, here it's explicitly put in, but you can also put it in as a file in case you're running on very large systems. It's not easy to have 10,000 lines in here, so you can read the coordinates on a file as well. Okay. So the parameters is set for each of the type of elements that you have and the specific coordinates that you actually have for the system. Final block for actually activating the Raman calculation is in the AO response calculation, where again the keyword Raman will tell you that it will actually do a Raman calculation together with geometry and frequency. So it's going to do a Raman calculation based on numerical differentiation. Okay. Frequency, again, the frequency which you can actually calculate the Raman scattering, and lifetime parameter here is the lifetime needed to calculate the response properties on resonance. This is in atomic units. This is about 0.1 eV, which is a reasonable value. So this is a molecular lifetime for that. Which means the combination of these and the DIM-QM will allow you to then do a Raman calculation for such a system. So you can look at the output file for the system. So again, it's going to run through the same procedure for running a Raman calculation for the free molecule. In each cycle, it's just going to do a DIM-QM. So there is general information about the discrete interaction model, exactly what settings you use. It's going to give you about the QM system and the coordinates for the DIM system and parameters that you use and the volume of the system. This is going to go through the standard SES cycle, and in each cycle is going to actually solve the interactions between the QM, and that's what's printed out here in the whole into dipole moment. Into this. And at the end of each cycle, you have the DIM-QM results, which give you the polarization energy, both due to the electronic part and the nuclear part. You get dispersion, repulsion term, and you sum these up to give it the fundamental and polarization term. And your whole interactions energy between the DIM-QM energy and the total induced dipole moment into the DIM system due to the molecule is printed here. Okay. This is going to do this then for solving the response equations again here in AO response. And again, it's going to print out the induced dipole moment in the DIM system due to the interactions with a metal nanoparticle. If you scroll down to actually looking at the results, it's first going to print out the polarizability of the molecule on this metal nanoparticle. Both have a real component and an imaginary component, and it's also going to print out the polarizability of the metal nanoparticles, the DIM system here, and a real part and an imaginary part, and then it's going to give you the cross section of all this. Okay, and then it's going to do the same type of calculations for the numerical displacement along the coordinates, which is the standard way of doing Raman calculation based on numerical derivatives. And at the end of that, you're going to print out the polarizability derivatives. So here you're going to have the frequency and the derivatives, and connected here is the Raman scattering factors, again, real and imaginary, and the total, and total is related to the observable for this. So for the system, if we actually look at the spectra, you can see that this is again N2 on the metal nanoparticle, and you see here you have a resonance here for the one mode for N2 stretch. If you do comparison, just look at the Raman spectra of the free N2 molecule here, you can see there is this huge enhancement to the surface field here for this system. You also see, you can actually see that here you have the variational frequency of 2,335 wave numbers, where you actually do have it shifted to a little longer wavelength here, 3342, again due to the interactions with the metal nanoparticle, which take into account here. Okay, so this is sort of illustrates the basics of running these simulations. So it's a little bit about setting up an actual DIMQM calculation, mostly related to setting up these three blocks, the DIMQM specifying what type of simulation is, the DIM4 gives you the parameters for each of these atomic atoms and the coordinates for the metal nanoparticle, enable response to specify what kind of response properties that you need for calculating the molecule. So I'm going to show you a few examples that have been calculated all using the ADF code. So here's just an illustration of calculating the polarizability of butene on a metal nanoparticle as a function of size of this metal nanoparticle without the local fields, including it with local fields. And you see that the polarizability with local fields increases drastically as the size of the nanoparticle increases, and then saturates right around 100,000 more, which is about 20 nanometer diameter. Whereas without the local fields, you see that you get a saturation pretty early on. So again, because the image field is short range and the local field is a long range effect. Okay. So we really need to be able to treat large metal nanoparticles using many atoms, and here solving these response equations becomes complicated for very big systems. So there have been implemented a fast solver using the Cartesian cell multiple method in ADF. So here's an example of that. This is the direct simulation. This is one we used for the N2 case, which is fine for systems below 5,000 atoms, where you can solve everything in memory. Everything else really becomes impractical and need to do this. So there is a brute force linear solver which scales quadratic the system, and there is this cell multiple method implemented either at single level or multiple level with different grid sizing. That really makes solving this linear equation scale n log n. But you can see about in a far range that you actually get close to a linear dependence for these large systems. But again, the time scale is large for systems above 100,000 atoms, and these simulations become time-consuming to do. But you can do simulations up to about 1 million atoms, So here is the Raman scattering for the two main modes, pyridines, the two ring-breeding modes, as a function of distance to the surface. So, with size of the metal nanoparticle. So we see here in blue is the MQM calculations for both these modes, and here in the straight line, with perfect agreement here, is actually the local field felt by the molecule at the nitrogen atom here, in this case here. Okay. And see that each of these have a different scale factor, again, because the molecule actually feels the field differently depending on these vibrational modes. That's actually taken into account in the dim model, but this standard electric field, there's no information about the normal modes. It will be identical in these two cases. So the radius about 20 atoms is about 1 million atoms. That's about where you get saturations of these curves. And again, the distance effect here is this is pyridine on a silver metal nanoparticle and a gold metal nanoparticle as a function of distance. This is an 8 nanometer particle. And you see, again, blue dots are the MQM calculation, and the red line are the electric field enhancement. And when you see you're far away from the surface of the metal nanoparticle, you really are described well by this electric field. On average, once you get close to the metal surface, you start to see deviation by this e to the fourth method, due to the fact that you both get a reduction of the electric field at the surface, and you also get field gradient effect as a clause here that's taken into account the fact that the electric field is inhomogeneous over the distributions of the molecule, and here bonding distance is stripe line here. So you really are in these regions here, where the MQM describe different results of what you get from a simple e to the fourth type mechanism. And the importance of these inhomogeneous electric fields on surface enhanced spectroscopy has been observed for a long time, but again, re-emerging in literature due to the standard selection rules that we are familiar with. Actually, it's broken when you are either a junction between metal nanoparticles or here carbon nanotubes, and between these very inhomogeneous electric fields. The one way of describing this is that induced dipole moment in homogeneous electric field is given by polarizability. But if you look at an inhomogeneous electric field, you have to have these dipole quadrupole, and you also have the magnetic dipole, so electric dipole induced by a magnetic field. You have to take that into account. So if you look at Raman scattering in an inhomogeneous electric field, it's given by our standard electric dipole term, but there's also quadrupole terms and magnetic dipole terms. And all of these can be described and calculated within the AO response module, and you can address them with sort of a local field enhancement. And here's just an example of doing that for benzene on a metal nanoparticle. Here's the experimental factor obtained from Moscowitz. Here's normal Raman scattering, and you see many of the peaks that are found experimentally not seen in free molecules because they're IR active modes and hence should be silent in a normal Raman scattering. If you do search calculation where you only look at the electric field component, you see these modes are also absent. Okay? And only when you take into account the electric field at the surface of the nanoparticle is inhomogeneous to actually start seeing these modes appear, which means you have to describe sort of this atomic roughness on the same dimensions of as your molecule is. So one of the major advantages of using the MQM method is that if you do the Raman calculation for the system, all these field gradient effects are naturally incorporated into the model. Okay. So here's an example of doing pyridine sort of on top of a needle, so the edge of a metal nanoparticle here, and you see the MQM calculations here. You see 3 dominant modes, if you do a SERS type calculation where you only consider the electric field, you see that these modes here are not appearing and these other modes are dominating. Okay? And once you actually do the SERS calculation again, where you have the electric field and the field gradient, you see that you get the same modes you see in DMQM. Okay? So in a DMQM calculation, all the interactions between the molecule and metal nanoparticles are naturally derived, even for these atomic type systems where you have very inhomogeneous electric field, and to actually play an important point in determining selection rules and surface enhanced Raman scattering. So with that, I would just like to wrap up. I hope to have shown you some of the capabilities that the DMQM implementation with an ADF in fact can do, and especially leads to go beyond the standard P to the fourth type of approximations that we use to describe surface enhanced Raman scattering, and importantly, it includes field gradient effects directly into these simulations. And hybrid methods such as the DMQM model, right, that really combines electronic structure theory and extradynamic simulation, would allow to describe a detailed atomic structure of these metal nanoparticles and all these interactions between this, which is relevant for describing surface enhanced Raman scattering. So again, I just want to acknowledge the people that actually did implementation. Most of the work implemented here was done by Seth Morton's PhD. Seth Morton is here. The gradients to do the Raman calculation was implemented by John Payton, and all the work on field gradient effects was current graduate students of mine. So we call high funding for this were given by NSF. And with that, I would like to thank you for listening, and if you have any questions, feel free to contact me or Fedor at the email address. Thank you.